Okay, so separation of variables, this time is the major league edition of what you did on the first test. First test, you're doing the low-level separation of variables. This one, we got separation of variables for partial differential equations. So what's going on with this one is we use it when it gives us, most of the time it'll give us some function u. And it'll say that function u is dependent upon functions x and y. So in this case, functions capital X and capital Y, where capital X itself is a function that is dependent upon variable x, lowercase x, and function y is dependent upon variable y. So things get kind of complicated because we got a lot of functions, we got a lot of variables going on. And the question, a lot of times it'll tell you that u, the derivative with respect to x, is equal to something, u with respect to y is equal to something, and this is just the basic breakdown of what things look like. If u is just equal to function x times function y, then our use of x is just x prime y. Our double derivative with respect to x is just x double prime y. So you can see that whatever we're taking the derivative of that function, just we take the derivative of that function. You don't have to worry about anything bigger than that. It's just what's written on the board. It's as simple as if we're taking the derivative with respect to x, we throw a prime next to that function, capital X. Does that make sense? It's just very basic, and we'll jump into a problem where, again, I have all the steps written out, and we'll walk through step by step where the hell lambda comes from and what the hell it means, and all that good stuff. So I'm going to do it over to you so we don't have some space. So this question was spring 2017, question 3. It says, use separation of variables to obtain a problem for, it gave us x, where this is a lowercase x. du dx is equal to du dy. So this is a lowercase x, and it said use separation of variables to obtain a product solution for that thing. So the first thing is, I don't like this du dx, du dy. It gets confusing, it gets annoying. So what I'm going to do is I'm going to substitute those things that I wrote up there for that. So I know that du dx just means I'm taking the derivative of u with respect to x, which means I have this first term on the top left. So that means that this is going to become x, capital X prime, capital Y. And my du dy is just going to be equal to x, or capital X, capital Y prime. The next thing that you want to do, so like the next step that I have written out, is you want to get the term with the x prime by itself. So we want to have everything that's dependent upon x's on one side, everything dependent upon y on the other side. Hence the separation of variables. So what I'm going to do here is I'm going to divide this side by, I want to divide by y over here. So that way I can get rid of this y. But I want to get rid of this x on the right side, so I'm going to divide by that as well. So what I'm going to be left with is these y's are going to cancel out, these x's are going to cancel out, and I'm going to have lowercase x times capital X prime over capital X is equal to capital Y prime over capital Y. The next thing that I want to do, I don't remember the mathematical reason or the proof for this, but I know it's just a thing you got to do, and you probably don't even want to know the proof. But we set this equal to negative lambda. This is where our fun lambdas come in, the beginning of the end. So we set this equal to negative lambda. And what we essentially have here is we just made two equations. Because I know that this x term is equal to negative lambda, and this y term is also equal to negative lambda. So what I do with that is I break each one out into a separate equation. So I'm going to say, let me get some colors involved. Do some green, some purple. I'm going to do all of my x terms in green. So I have x, capital X prime over capital X is equal to negative lambda. And then I have capital Y prime over capital Y is equal to negative lambda. So the idea now is each of these are just first order differential equations, ordinary differential equations that we're used to using, because we have some function x, where we have a derivative. Here we just have that function x. Here we have variable x, and that's just some constant lambda. So I'm going to rearrange it so it looks like something that we're used to seeing. So first I'm going to take this capital X, I'm going to multiply it to the other side. So we're going to have lowercase x, capital X prime is equal to negative lambda capital X. And I'm going to move it over to the other side. So we have lowercase x, capital X prime, plus lambda capital X is equal to 0. And then essentially what we have right now is this is our function term, our capital X. We're used to seeing that as our y. So like you can think of this as like y prime, that's our y. We like to have our y prime term by itself. So I'm just going to divide everything by that lowercase x, and I'll be left with capital X prime plus lambda over x times capital X is equal to 0. And now this looks really weird, but like I said, you can think of this as just being what we're used to seeing as y prime plus some constant over x, y is equal to 0. It's not that bad. If I had some number in there for x, you would know how to solve that. That wouldn't be that difficult of a problem. It just looks a little funky because we're dealing with capital X's and lowercase x. So now I'm going to hop over to my y's, and this one's actually going to be a little bit easier because we don't even have that lowercase x in front. So we're going to multiply by y on the other side. We'll have capital Y prime is equal to negative lambda capital Y. And we have y prime plus lambda y is equal to 0. So again, just another first order ordinary differential equation. So what we were able to do with our separation of variables is we took this weird partial differential equation where we had u dependent upon x and dependent upon y, and we made it into two different first order ordinary differential equations. So now what we're going to do is we're going to solve this one and get, at the bottom, we're going to get function x is equal to something. And then we're going to solve this one. We're going to get function y is equal to something. And I know that in this problem it said my u is equal to x times y. So I'm just going to take this something, multiply it by that something, and I'm going to have my answer for the whole problem. So let me erase these squiggles so we can actually figure out what they are. I'm going to do that. So now, going with my x's, I have x prime plus lambda over x capital X is equal to 0. So I want to be able to just figure out what my x is equal to, what my capital X is equal to. So I'm going to rewrite this a little bit, because now it's just at the point where I'm just trying to solve this. So I'm going to rewrite this as d capital X over d lowercase x plus lambda over x capital X. So what I want to do is, I'm going to take this and I'm going to move it over to the other side. So that way I can get d capital X over d lowercase x is equal to negative lambda over lowercase x capital X. And now this goes back to separation of variables from the first test, where I want to get all of my capital X's on the left side and all of my lowercase x's on the other side. So I'm going to take this dx and I'm going to multiply it to this side. I'm going to take this capital X and I'm going to divide it over here. And what I'm left with is 1 over capital X dx, sorry, d capital X, is equal to negative lambda over lowercase x d lowercase x. And now I can just take the integral on both sides and I'll have an answer. So the integral of 1 over x is just going to give me ln of x. And on the other side, I'm going to have a similar thing. I'm going to pull out this negative lambda, and I have the integral of 1 over x is going to give me ln of lowercase x. But then I have to remember to do a nice plus c. The plus c is coming back to bite us. Coming back from that first test, it's rearing its ugly head again. So we have to include that plus c. So now I'm almost there, but I want to find what x is equal to, what capital X. I don't care what ln of x is equal to. So I have to do a little bit more algebra, and what that entails is raising each side to, or doing e to the power of each side. And what that allows us to do is we then have capital X on the left side, because e to the ln of something is just that something. So then this right side is going to be the right side. I know that this is really the same thing as this exponent is the same thing as negative lambda ln of x minus lambda c. And I can take this lambda and bring it into that exponent. So I can say that this is ln of x to the minus lambda. So when I do e to that power, e to the ln of x to the negative lambda just becomes x to the negative lambda. And I'm going to have times e to the minus lambda c. I know that's a little tricky. I know it's technically supposed to be absolute value. It like never matters. It never ends up mattering. Technically, like mathematically, you should, but especially when you then take like e to the integral, it just goes away anyway. So I always leave it out. It's a bad thing that I do, but it never really ends up mattering. I would say no, just because lambda has significance, so we don't want it to get absorbed into something else. Technically, it would just be a constant because lambda we know is just a constant, c is just a constant, so it would just be another constant. If you're going to do that, I would write it as like c1 or write it as d or something like that, because it's not the same constant as c, it's a different constant. But I would keep the lambda there just because lambda has significance even if it is just a constant. But either way, this is what we get for our capital X. This is the function for capital X that makes this differential equation true. Now, we need to figure out capital Y. The nice thing about capital Y is it's going to be much simpler than this. We're not going to have to worry about taking integrals, we're not going to have to worry about fancy stuff like that. Because all we have is y prime plus lambda y is equal to 0. We set up our auxiliary equation of m plus lambda is equal to 0. Therefore, I know m is equal to negative lambda, and my capital Y is equal to c e to the negative lambda lowercase y. Does that make sense? That's just auxiliary equation, plugging in my exponent, there we go. And now coming back, I know that u is equal to x times y. So I can take that x, I can take that y, multiply them together, and I have my answer. So it's going to be x to the negative lambda times e to the negative lambda y plus c. And that's just combining those two terms. I don't know why I didn't include, is that constant? I guess because I just assumed it would get absorbed into that C there. So I kind of did a similar thing. But anyway, this is your final answer to the separation of variables problem. Does that make sense? Yes.
So can we just take the e to the, we can't just take the e to the negative lambda c and constant k?
You probably can. I'm not 100% sure, just because.
And if we did that, we could put constantly saying that e to the negative lambda c
I would get it. If you were to do it, I would like write somewhere on the side like e to the negative lambda c is equal to just like some other constant. I'm hesitant to do it because lambda does have significance, and I don't know if they're gonna like take off points because you got rid of a lambda. I don't remember, but theoretically it does make sense. Yes.
If you multiply those two together, wouldn't your first layer
So this isn't x times that times that. So it's not double distribution, they're just all multiply next to each other. Yeah. Yep. So we have y prime plus lambda y equals 0. So we just write our auxiliary equation. M plus lambda is equal to 0. This one we don't even have two roots for them, we just have one. So we get m is equal to negative lambda. So we just have y is equal to c, and this would just be like e to our n x normally. But since our variable for this case is our lowercase y, that's why we have that lowercase y. And then that shows up with this e to the negative lambda y.
And the x one, that lambda was divided by x.
If lambda wasn't divided by x, it would actually be a lot easier because you would get to this point, you would just have, well, yeah, you would be able to do the same exact thing that we did here. Yeah. This step before the integral, I got all of my capital X's on one side and all my lowercase x's on the other side. So I had a d lowercase x here, so I multiplied that to the right side, and I had a capital X on this side, so I divided that over here. And that left me with 1 over capital X times dx, d capital X. And on the right side, negative lambda over lowercase x times d lowercase x. You're welcome. Yes?
Sorry, C divided by Y.
did in these notes. I think I assumed that it would get absorbed in that. I don't know if that's fully correct, but that's what I did. So that's what I'm sticking with. No other questions. We're going to go with some IE values. I'm going to blow your mind by teaching you a better way to do it than they taught you.